I'm going to go and put a point at 9, 2, because I have 9 edges and 2 triangles. So now you can tell me in the chat or just annotate directly on the grid, where is your graph? So how many edges and triangles does it have?
Sorry for interruption. Annie, do we have your permission to record a lecture?
Yeah, that's fine.
Thank you.
But Ali, tell me, how many edges and triangles do you get in your graph?
In this graph, or
in a graph, any graph, your favorite graph on 7 vertices?
On 7 vertices, that's complicated. Favorite graph is the empty one.
Choose the empty one. So how many edges and
Like
triangles do you have?
10 edges and 3 triangles.
I'll say that again, Rodolfo. I didn't hear you.
Yeah, sure. Sorry. 10 edges and 3 triangles.
Okay, so you're right here.
Yep.
Ali, where are you?
So,
also the cycle, so that would be 7 edges and no triangles.
True, that's one possible. Could have the complete graph, right?
Yeah.
And it's not actually there. I just drew 1.21 and 25. So up here. All right, so we could each come up with a graph. And so if there were more of us, we could come up with even more graphs. And so we could ask, like, where will all these points fall? And so if there was enough of us, this is what we would get. So if I were to draw all graphs on 7 vertices and count how many triangles and how many edges they are and plot that, I would get one of these points. And so now we could say, well, let's do the same thing for 8 vertices, 9 vertices, however many vertices as you want. And so as you get more vertices, like your axis, you would have to keep going further and further, right? Like if you were to look at, a graph with n vertices, then there can be up to n choose 2 and n choose 3 edges and triangles, right? So this goes bigger and bigger. So somehow like our 7 vertex graphs would all be down there, like near the origin. So maybe you would say, oh, let's look at densities instead, right? Maybe, like all complete graphs are kind of alike in a certain way, right? So some people prefer densities. But so these graph profiles, the idea is to understand these shapes in general for any graphs, either in terms of densities or in terms of numbers. So we'll define that carefully in a moment. But to do that, we first need to kind of agree on what we mean by counting. So how do we count things? Well, there's 3 ways of counting, maybe more, but these are the 3 ways that I know. So let's say that you have 2 graphs H and G. And now you look at maps from the vertex set of H to the vertex set of G. If your map is injective and it's then edges of H to edges of G and non-edges of H to non-edges of G, then what you're counting are the endorsed subgraphs of H and G. So these maps, however many maps you are that are just in this way, will give you the number of induced subgraphs of H and G. Now, if you don't care about sending non-edges to non-edges, if you only care about being injective and sending edges of H to edges of G, then we're counting subgraphs of H and G. And then finally, if you don't care about being injective, you just want to send edges of H to edges of G, then we'll call that counting homomorphisms of H and G. So let's look at an example to make that clear. So let's say that this is my graph H, and this is my graph G. And so I want to find a number of induced subgraphs of H and G. So I need to look at all the maps from the vertex set of H to the vertex set of G that sends edges to edges, non-edges to non-edges, and that are injective. Any guesses on how many there are? Making you work so hard, and there's only 4 of you, so like it's even more stressful.
In H, there is only 1 node H, so there is only 1 assignment in G because there is only 1 node H there. So at least we know easily how to compute the node H. Where does it have to go?
So you know exactly, you're completely right, Rodolfo, that we know exactly where the non-edge needs to go, right? So like, but does that mean that there's only one choice?
I was seeing two choices, so
Okay.
yeah.
Alison is seeing two choices. Anybody sees more than two? It's like a betting game of going higher. So there's actually four, because we want to think really about, you know, the maps from vertices of H to vertices of G. So my check mark, right? So like we can use Rodolfo's observation that, okay, we know that my check mark and my heart need to go to the non-edge, right? But it could have gone the other way as well, right? It could have gone, my heart could have been here and my check mark could have gone here. And then my last vertex, no matter what of these two choices I've done, well, there would be two choices for it. It could go there or there. So in total, there's really four, right? Because so Alison, I think, you know, for example, you were counting this as one choice, but there's really this and this. You can flip it, the two endpoints. So you're really counting maps from the vertex set to the vertex set. Okay, so we have four. All right, so what about if I want to count the number of subgraphs? So now I'm again looking at maps from the vertex set of H to the vertex set of G, and I want it to be injective, and I want to send edges to edges. So now all of a sudden I have way more choices, right? So the four previous choices are still there, but I can also have that my non-edge can go to an edge, right? So any guesses on what the total will be in this case?
So there are four more at least.
Anybody says more?
I said
Yeah, it looks like four more.
Nobody sees more than four more.
no, there are many more. Sorry. So all the triangles will give rise to, I don't know how many, like 6.
Yes, exactly. So each triangle, right, you can have, like, you have the 3 pairs of 2, and for each pair of 2, you can go like this or like this. So then each triangle gives you 6 more choices. So, okay, so that means that you had your 4 old ones plus 2 times 6 for the 2 different triangles. So we're at 16. All right. And then finally, we have the number of homomorphisms, where I look at all maps and they don't need to be injective. That's an edges to edges. So certainly my 16 previous maps will still hold, but now my map doesn't have to be injective. So, and I just care about sending edges to edges. Anybody sees how many new maps I get that work out?
So sorry, I need one quick question. So
Yes, please.
any edge of H can go to any edge of G, right?
Yeah.
So yeah, we have 2 edges in H, and there are 5 edges in G. So it's 5 times 5 is times 5. No.
Oh, well, I do want the edges to go to edges. So now
okay,
you're
okay.
counting all maps in total.
Yeah.
But I want the edges to actually go to edges.
Okay.
So for example, I could get my star going here and my heart and my my check mark going to the same place, right? So then my star edge is still an edge. My star heart is still an edge as well, right? So for every edge of G, I'm going to have 2 different ways of sending H just to that one edge, right? Either I could go like this, or I could have gone up in this case, right? So bringing them together. So I have 10 more in total. So that means that in total, I am now at 26. Does that make sense for everybody? Any questions about these 3 ways of counting?
No, we're good.
All right, good.
Thanks.
So we could have done the same thing, but with densities. So we can have the induced subgraph, the subgraph, or the homomorphism density between H and G. And I just take the probability that a random injective for induced subgraph and subgraph, it doesn't have to be injective for homomorphism, map from the vertex set of H to the vertex set of G yields an induced subgraph, or a homomorphism. Right, so now I just need to think about how many injective maps are there in total, not necessarily sending edges to edge and non-edges to edges. Well, okay, my first vertex of H can be sent to 4 vertices, my second to 3, and my last one to 2 if I have an injective map. So in total, there's 24 injective maps from the vertex set of H to the vertex set of G. 4 gave me an induced subgraph, so my induced density is 4 out of 24. For my subgraph density, same thing, total number of injective maps doesn't change. So I get 16 out of 24. And then what Rodolfo had seen before, the total number of maps, if I don't care about my maps being injective. Okay, so I have 4 times 4 times 4. So I have 4 to the 3 possible non-injective maps from the vertex set of H to the vertex set of G. Well, some of them are injective, don't need to be injective. All right. So these quantities are all related, right? So you might have a favorite way of counting. Maybe you're just like induce is way better, or subgraph is much better, or homomorphism is much better, but they're all related. So if you look at the subgraph density, it's just a Möbius transformation away from the induced density. And if you look at very large target graphs G, where the number of vertices grows to infinity, then the difference between the subgraph density and the homomorphism density goes to 0, assuming that H is fixed. So H has a fixed size, and you let the size of G grow to infinity, then really asymptotically, these two quantities calculate the same thing, right? So if you understand one, you do understand something about the other, at least asymptotically. So we're going to be talking mostly about homomorphisms today and homomorphism densities, but really, just keep in mind that they're all related. Ali, do you have a question?
Yeah, can you come back to previous slide? I just want to know the definition of density. Okay, the number.
So you take the number of maps that does work out over the total number of maps you could have had. Okay. Right. So in the first 2 cases, you only consider injective maps. That's why you're over 24. And for homomorphisms, you really consider all possible maps from the vertex set of H to the vertex set of G. And the 4, 16, and 26 are the numbers we had already counted. Yeah. More questions about our ways of counting, and specifically homomorphism? Just want to make sure we're all good on homomorphism, since that's what we'll be using. All right. So now that we know how we want to count, we can define exactly what we mean by a graph profile. So let's say that I have a collection of some L graphs, H1 through HL. Then the graph density profile of my collection is going to be the closure of the set of vectors that record the homomorphism densities of my HIs in some graph G. Right, so I can look at any target graph G, and I calculate the density of all my HIs in there. I create a vector out of that, and then I take the closure of all such vectors. And the number profile, the graph number profile, is going to be similar, but instead of densities, I'm just going to take the set of vectors that records the number of homomorphisms of H1 through HL and G. Right, and so this is kind of what we were doing at first, right? When we were taking the edge and the triangle being our collection U, and you were counting the number of copies, right? But we hadn't decided on a way of counting yet. We kind of knew what I meant, and so we all agreed on the same way. But now we're saying, okay, count the number of homomorphisms and take all these vectors. That's going to be the number profile. So here's what this can look like. This is the density profile for the edge and the triangle. Right, so we had seen the edge and the triangle when we were playing with it, but we didn't look at density. So here we're looking at densities. And so this picture was, conjectured to be true for quite a while, but Hasbahov is the one who showed it to be true in 2008. He used flag algebras and sums of squares to prove that this was correct. And I really love this picture. So you have Mantel's theorem at the bottom. If you've taken some combinatorials class, you might know Mantel's theorem that says that if you have no triangle in a graph, then the maximum edge density is 1/2. So no triangle in a graph means that I'm on the x-axis, right? My triangle density is 0. And yes, the maximum edge density is 1/2. And then I have over here, I have Turon graphs. So graphs that are k-partite, complete k-partite graphs with pairs that are as equal as possible. And then I keep having these little concave bits. I just didn't draw all of them. So I think it's a really cool picture. And so understanding such a graph profile, essentially what it means is you try to understand all polynomial inequalities that are true, right? So for example, this polynomial inequality says that the edge density cubed minus the triangle density squared is greater or equal to 0. Right, so I can think of this as certifying the non-negativity of some inequalities. So wonderful picture, I love it. But really, we know very little about these things, right? So in one picture, we get Mantel's theorem and many other interesting things about extremal graph theory, but edge and triangle is one of the very few cases that we know. So we know density profiles for edge and complete graph. Right, so edge and triangle was done by Hasbuhov, then edge and complete graph on 4 vertices was done by Nikiforov, and then Hayat generalized that for any complete graph. I think we know it for one other pair of graphs, like path of length 2 and a triangle. It's not known for any triple of graphs. So, okay, nice picture, but we know very little.
Is that semi-algebraic? Sorry.
Say that again, Ali?
Is that a semi-algebraic set? Do we have a proof for that?
So we don't actually know how bad things get. So in this case, it is, but it doesn't have to be semi-algebraic. And in a certain way here, you have countably many inequalities, so no. But all the inequalities are polynomial inequalities. And then there's this paper by Hatami and Nahin where they find this graph profile and then they slice it and project it down and they get the shape that is almost nowhere differentiable. So, but they slice it and projected it, so really, you know, that doesn't mean anything, but it's yeah, we don't know how bad it can get, right? So here in a certain way, it's not too bad because yes, you have infinitely many polynomial inequalities, but okay, they're all polynomial inequalities.
But and it is just going back to Ali's question. It is so in that corner on the top right, you didn't draw all these little kings.
Yeah.
So
and there's countably many.
That's and getting smaller and smaller, right? So in fact, that point is not even, because I was thinking that maybe it's locally semi-algebraic, meaning that if you take a neighborhood of every point is always is a semi-algebraic set, but that point is not even locally semi-algebraic.
Yeah, no, you're completely right that because we keep having these smaller and smaller intervals, yeah, it is not. But I do think that in this case, you're right, that it's locally semi-algebraic.
But that upper right point is not even locally semi-algebraic.
Yeah, that's true. And yeah, we really don't know how bad it can be. So like edge and triangle is kind of the simplest to collection that you could have, right? And already you get this somewhat complicated picture. Yeah, no, that's a great point. So yeah, so we really know very, very few. We don't know any triple of graphs, right? So even though we know edge and every complete graph, we don't know like edge, triangle, and a complete graph on 4 vertices or anything like that. There are some simple true inequalities that cannot be written as sums of squares or rational sums of squares, right? So that's something that we showed in previous papers. So if you take the density of a path of length 3 minus the edge density cubed. We know that this is non-negative from different techniques, but it cannot be written as a sum of squares or a rational sum of squares. And just to give you an idea, what does a sum of squares look like in the setting? So this would be the proof that the path of length 2, the density of a path of length 2 minus the density of an edge squared is a sum of squares and thus non-negative. So you use partially labeled graphs. And so, yeah, you have a way of gluing them and then symmetrizing to remove the labels. So yeah, so it makes it different from the world of real polynomials, right? That there's not even necessarily a rational sum of squares. We know that it is actually undecidable in general to check whether a polynomial expression in either numbers or densities is non-negative on all graphs. And number profiles are more general than density profiles. So the pictures that I showed you was for density profile, and number profiles are more general, and it's easy to see that. So if I have an inequality involving densities of some graphs, so for example, here I have the density of a path on 6 vertices cubed minus the density of a path on 4 vertices to the power 5. Well, I can rewrite that in terms of the number of homomorphisms, just by the definition of homomorphism density. So the number of homomorphisms over the total number of maps. And so if I do that, well, the total number of maps, is just going to be the number of vertices to the 6 and to the 4 on the other side. And then with the powers, you can cross multiply. And you can also just realize that if I look at the number of homomorphism of a single vertex into G, I will get exactly the number of vertices of G. So I can replace, I can cross multiply and replace the number of vertices of G by just the number of homomorphisms of a single point in G. And then I get an inequality that involves only homomorphism numbers. So any density inequality can be written as a number inequality. The converse is not true, right? So I can only do it if my inequality is balanced in the total number of vertices on both sides. So, okay, so number profiles, we know even less. So one idea is to try to simplify our number profiles and our density profiles. And so we're going to use tropicalization to do that. So how does tropicalization work? So I have a log operator where I'm going to, if I take the log of a vector, I'm taking the log of every single component of that vector. And if I have a set that is in the non-negative orthant, well, I cannot take the log of 0, so I'm just going to take the log of the set intersected with the positive orthant. And so we can show that you don't lose anything important that way. So the tropicalization of some set in the non-negative orthant is going to be the limit of the log base 1 over k as k goes to 0 of my set. And now if you've never seen that, that might seem a bit weird. What is happening is that we're moving from, your normal polynomial ring with addition and multiplication becoming taking the max and or the min, depending on your setting, and adding. And so that's simpler than adding and multiplying. And so what we were able to show was that the tropicalization of the density profile is just the closure of the convex hull of the log of the density profile. So you don't need to take the log limit. You can just take log in whatever fixed base that you want and take the closure of the convex hull of that, and you'll get exactly your tropicalization. So it means that you get a closed convex cone. So again, we're starting with this graph profile that is very complicated. We don't know how bad it is. And after you tropicalize, you get a closed convex cone. That is much simpler. And so what are we keeping? What is the closed convex cone, retaining for the information? It's retaining, well, it's determined by linear inequalities that correspond to the binomial inequalities that were valid on your density profiles. So you're losing everything except for the true pure binomial inequalities. The same is true for the number profile, except that will be in the non-negative orthant versus the non-positive orthant, just because numbers are between 1 and infinity and they're integers, whereas here we're between 0 and 1, and we're half the numbers to start with. But so that's nice. So we go from a very complicated shape to a closed convex cone, and we still retain something. We retain binomial inequalities. So let's look at our very complicated picture that we had for edge and triangle. So we had this inequality, the density of the edge cubed minus the density of the triangle squared was greater or equal to 0, was the top inequality. And so that top inequality, once I take the log, just becomes, well, 3 times the log of the edge density minus 2 times the log of the triangle, right? And so if I plug that into this here, then I just get this nice inequality, linear inequality, right? And so I've lost all of the scallopy concave little bits. So I've lost all of the interesting things in this particular instance. So you might say, this is not very interesting. You lost everything that made this picture interesting. And that's true. In this case, we do. We lose information that we really care about. But if you take a second to think about problems from extremal graph theory, a lot of them are about certifying binomial inequalities. So if you do care about some problem in extremal graph theory where you're talking about binomials, well, that we are retaining here. So we are retaining something interesting in general, just not in this case. So let me give you an example of a problem from extremal graph theory where we retain something interesting, but maybe actually I should take a moment to make sure everybody is still on board and to see if there's any questions.
I have an unrelated question, or maybe not so related. Why is it called the tropicalization of this?
That's a great question. So it's called tropicalization because there was the first few people who worked on it was a group of Brazilian mathematicians, including Imre Simon. And so for whatever reason, I guess Brazil is tropical, and it ended up with the name tropicalization. But yes, one of the first people to work on this was Imre Simon with a group of other Brazilian mathematicians. And so that's where it came from.
I see.
I kind of wish we had called it Simonization, but more questions about tropicalization?
And so why do we define tropicalization of S that way? Why do we have limits?
Well,
yeah.
So we.
So where is that coming from? I mean, I guess my question is, where is that definition of tropicalization of S coming from?
I mean, it's really coming from algebraic geometry. So it's starting to be kind of a trend in algebraic geometry to tropicalize things, to simplify them. And so, you know, the limit is there so that you have certain nice properties in terms of, transforming your max and your addition into max and your multiplication into addition. And so you get all of these nice properties from being in the limit. If you didn't have the limit, there's many things that wouldn't work out. Yeah. But yeah, we did not come up with tropicalization at all. Just to be very clear, it's been more and more used in algebraic geometry in general. It hadn't been used a lot in real algebraic geometry, but in algebraic geometry is a well-established technique. All right, so let me show you a problem from extremal graph theory that is related to the type of information that we retain from taking the tropicalization. So the homomorphism domination exponent is written as the HG of H1, H2. H1, H2 are two graphs. and it records the maximum value that C can take, so that the following inequality is true for all graphs G, so that we have that the number of homomorphisms from H1 into G is greater or equal to the number of homomorphisms of the H2 into G to the power C. So what is the maximum C that will make sure that this is always a true inequality for all graphs G? And so really a lot of problems in extremal graph theory do have that form, even if they're not written in that way. So Sidoranki's conjecture has been around for 30 plus years now, I guess, or about 30 years. And it states that the homomorphism density of a bipartite graph H and G is greater or equal to the homomorphism density of an edge to the power of the number of edges in H. So it's known to be true for many classes of graphs, but the whole conjecture still eludes everybody. And so you can rewrite this as saying that I am looking at the homomorphism domination exponent of these two graphs. So H, my bipartite graph H, with 2 times the number of edges in H minus the number of vertices of H disjoint copies of one vertex. So that's my H1, and my H2 is a single edge. So if I could show that the HG is a number of edges in H, that's exactly showing this. There was the Adler-Simonovich conjecture that stood for a long time that stated that the homomorphism densities of a path with k vertices to the power L minus 1 was greater or equal to the density of a path with L vertices to the power k minus 1. And so again, this can be rewritten as a homomorphism domination exponent problem. And so it's kind of underlying in the picture there. The term was coined by Kobarty and Hussman, but yes, a lot of problems, were really problems of this form. So in 2011, Kobarty and Hussman showed that the HGE can be computed through a linear program if H1 and H2 are both chordal and series parallel graphs. So that's very nice. Linear programs are easy. So, and they wrote, what the linear program is. So that's wonderful. And so we used the results of Kobarty and Hussman to show that the Adler-Simonovich conjecture is true. For a few days, we thought that we were the first people to solve it. And then we realized that Matt Saglam had already done it in 2018. And so too bad. But we did it in a completely different way using Kobarty and Hussman, and it does make it very simple. So, you can really write it. It's just like proof is like a page. Anyway, we did want to push further. And so what we can do with the Kobarty and Hussman result is show that the tropicalization of the number profile is actually a rational polyhedral cone when my collection of graphs contains only graphs that are chordal and series parallel. So already, okay, we knew that the tropicalization was a closed convex cone, and now we're saying, no, it's a rational polyhedral cone. So you're starting to get something that is very nice and simple. And so we do wonder if that is true in general for whatever collection of graphs that you have. That would be really nice. And so far, every collection that we have been able to calculate has been in this way, a rational polyhedral cone.
Can I ask a question? So in algebraic geometry, tropicalization, I guess, would always produce something polyhedral. But the fact that it's polyhedral in this case is because the object, this NU, is not an algebraic object. And so that's why being polyhedral is non-trivial.
Yeah,
property.
no, it is definitely not a trivial problem here. And we would be ecstatic if it turned out that it is always polyhedral. Yeah.
This is because of the non-algebraicity of this
Yeah.
object.
Yeah, I don't know much about tropicalization in general for algebraic geometry, but yes, definitely in this case, it is not trivial. And a lot of people are very dubious that it will always be polyhedral. It would be very nice if it was. And so, but yeah, there are some nice properties. And so I do want to talk about the nice properties that are helpful, and maybe that in the end will help us prove more. But at the moment, we can only show the polyhedrality for very specific classes by actually calculating what is a polyhedral cone in general. We don't have any, we're very far from understanding generally why it should be polyhedral. So yeah, there are some very nice properties of the number profile and tropicalization that has helped us get these results. So the first property that is very nice is that the number profile and the density profile have the Hadamard property. So it's closed under component-wise multiplication. So the number of homomorphisms of H in G1 times the number of homomorphisms of H in G2 is the number of homomorphisms of H in some other graph, which is the Cartesian product of G1 and G2. It's also closed under coordinate-wise addition, since the number of homomorphisms of H in G1 plus the number of homomorphisms of H in G2 is also equal to the number of homomorphisms of H in some graph as well, which is G1, G2, where you have that G1 is one component and G2 is another component. And so from that, we can get that the tropicalization is max closed. So if I have 2 points that are in the tropicalization, then if I take the max component twice, that point is also within the tropicalization. So this is very helpful. And so this allowed us to show that any extreme ray of the dual cone of the tropicalization is spanned by a vector with at most one negative coordinate. So what this means is that the important binomial inequalities are the ones where there's only one type of graph on the smaller side. So for example, this is an inequality about the number of homomorphisms of paths of certain lengths that had been proven, years ago. And so this type of binomial inequality is not important. We know that's going to be redundant because it involves two graphs on the smaller side. And so that's kind of good to know, right? So we're kind of like, okay, the only important binomial inequalities will only have one graph here. It can have more graphs on this side, but on this side, there can only be one. And so that was very helpful information to use to be able to calculate certain tropicalizations for certain classes of graphs. So let me show you like a simple example of how to calculate a tropicalization. So let's say that I have the collection where I have all complete graphs on up to L vertices. So you remember that for the density profile, when you edge versus any complete graph, and then number profile is even more general, and certainly we didn't know if we took, 3 of them, we would have no possibilities of understanding anything. So here we take all the way up to complete graphs on L vertices, and we calculated tropicalization. And it's very simple. So the tropicalization is equal to this cone, where defined by the inequalities here, where the yi's are the logarithms of the number of homomorphisms of ki into g. So to prove that this is the correct cone, the proofs always work the same. Sometimes they're much harder, but the steps are the same. So we want to first show that the tropicalization is indeed within the cone. And so here, how do we show that it's within the cone? Well, we know that, we know some inequalities about homomorphism numbers of complete graphs. We know the Kruskal-Katona inequalities, for example, right? So we know those hold. And so if I take the log of these inequalities, I get exactly the inequalities that I have up here. And so I'm just missing the one when I is equal to 3, but that one is easy to prove. And I also have this extra inequality that I need to make sure is true, but I know that I'm intersecting with the positive ortho, so I know that the number of homomorphisms of KL into G is greater or equal to 1, which if I take the log, gives me the last inequality that I needed. So because of that, I do know that my tropicalization sits within this cone. So now I need to show the reverse way. I want to show that the cone sits within this tropicalization, and then I'll be done. And so to do that, well, I'll calculate the extreme rays of my cone and then realize them and show that they are in the tropicalization in that way. So calculating the extreme rays of this cone is pretty easy in this case. We have L constraints and L variables. And so it turns out that these are the extreme rays. They look like 1, 2, 3, all the way to I, and then a bunch of zeros. And so you can see that they're extreme rays because they satisfy all but the ith constraint at equality, which it still satisfies. So we're good there. So now we just need to find some graph that realizes these rays. So to realize Ri, I'm going to take Gn to be the I-partite complete graph where each part has n over I vertices, so a Turin graph, with one disjoint copy of KL. And so I need KL because I need to make sure that there's at least one complete graph of size L so that I don't get any zeros in my number anywhere. So then as the number of vertices goes to infinity, I could calculate what is, the log of the number of homomorphisms of Kj and Gn over the log of n. And so if j is smaller than I, then I do have some copies. If j is bigger than I, then I don't have any copies. And so I'll only have that one copy or those few copies within that disjoint copy of KL, but nowhere else. And so as n goes infinity, that will go to 0. And then if I take the time to check this, yes, this will go to j. So, okay, I got exactly the vector that I needed. So I know that my RIs are realizable. And so that means that my RIs are in the tropicalization. And so Q is equal to the tropicalization. So this is, the general form, you show that your cone sits within the tropicalization and your tropicalization sits within your cone. Then you're done. But so the nice thing that we know from this is that every pure binomial inequality that involves complete graphs can be deduced in a finite way from the inequality that we have above. So for example, we have the general Kruskal-Catona inequalities where you don't have to have that Q and P are just one away from each other. And so, yeah, you can recover them from the ones where they're just one away from each other. But any true inequality, any true binomial inequality can come up involving complete graphs will be recovered from just those binomial inequalities. So we were able to compute the tropicalization for a few cases besides that. So we were able to do it for even cycles, odd cycles, for stars, for paths, and this was definitely the hardest case we've done. We had to have a lifted representation. And I'll say a few words about consequences of paths. We were able to do it for hypergraphs as well, and some non-graph objects like the number of k-faces of simplicial complexes, for matroids. Yeah, matroids, it was even more interesting because it doesn't even have the Hadamard property. And so, yeah, in all of these cases, we got this polyhedrality phenomenon, and more than polyhedrality, rational polyhedrality. And so we do conjecture, we hope that it is true in general. So let me just say a couple of words about the number of paths. So this was definitely the hardest form. So these were the different types of binomial inequalities that were needed. So they were the non-redundant, the essential binomial inequalities from which all other binomial inequalities involving paths can be recovered. And they have somewhat nice formats. So you kind of have log convexities phenomenons. You have some weak convexity phenomenons, and then you have non-decreasing and log subjectivity. But this is a lifted representation. And by that, I mean, so if you have a pure binomial inequality that is true involving paths, and it involves paths up to V vertices, then you'll want to consider these inequalities up to 2V vertices to be able to recover it. If I wanted to stick to V, I would have to have even more types of inequalities here, and things would get messier. So knowing all of this allowed us to give a solution to the Kabat-Zinn problem of computing the homomorphism domination exponent for any two paths of any lengths. our contribution is the first 2 lines. The last 2 lines were already known. And without wanting to throw shade at Kabat and Husman, one could ask, why couldn't they do it? Because in the end, to prove the inequalities that we had there, like we proved that this was complete and everything, but to prove the inequalities themselves, we used their technique. So why couldn't they recover this? And I think one of the lessons here is that there are questions that look natural coming from extremal graph theory, but really there are some messy projections happening. And so if you try to understand the whole object, like try to understand all the true relationships, that might be somewhat simpler than actually going straight for that natural looking inequality. Right, so here and then, you needed to have 4 cases and whatnot, so it ended up being messier. The other nice thing is that we also got a generalization of the Adler-Simonovich conjecture. So the original conjecture was for A is equal to 1, but actually it's true for any A that is odd, and all of these are actually essential inequalities. They're not redundant, so they're important ones. And we also got this new class, like this weak convexity type of inequality that, as far as we know, were known before. And so it was kind of nice to really get the full picture of what is important for PATS. So, all right, so I'm out of time. So I hope that, what you get from this talk is that, okay, tropicalization is very useful to study valid binomial inequalities. So any type of problem where you care about binomial inequalities, this might be useful, especially if you have the Hadamard property, right? So it's not just for graph and number profiles. Anything that has the Hadamard property will probably have some pretty nice properties, and you'll be able to say something. It's even more interesting if you have, other nice properties like being max close or min close. Definitely, then you'll get an even better handle. And so certainly for the case of graph and number profiles, it's helpful to solve some problems in extremal graph theory that involves binomial inequalities, which really there's a lot of. So I will stop here. Thank you.
Thank you, Annie. Let's thank Annie for this wonderful talk. We have like 5 or 7 minutes for questions, discussions.
I'll ask a question. So you have this conjecture about polyhedrality in general, right?
Yeah.
Maybe related to that, in the cases where you can prove this polyhedral, does it come with some bounds of some sort of the number of faces of the polyhedra in terms of the graphs?
So I mean, so in the case, well, so there's a general case for the chordal and series parallel graphs. That's when I haven't thought about how many faces you could have. Definitely for all the other ones, we have a very clear description, and so there you could count. Like it will depend, of course, on where do you stop, right? Because these are infinite families of graphs. But in terms of, okay, let's say that you go up to this to L, then certainly we can put a bound on the number of faces for those descriptions. And I think you should be able to do it for the Kabat-Zerasman through your linear program as well. But I'd have to think about it.
And do you think this is true, this polyhedral cone conjecture? So
I would hope so. So I mean, so the thing, so right, there's this result by Hatami and Nahin that, there's this undecidability result, right? And we even know that, like for numbers of homomorphisms, we know that even if you have just like a polynomial with 9 terms, it's undecidable, right? So here somehow we're talking about polynomials with 2 terms. Is 2 terms with no coefficients, right? So we're really considering pure binomial inequality. So there's no coefficients. Then is that easier? Is that all of a sudden like truly easier, because having a rational polyhedral cone would kind of tell us something that, yes, it is easier. I would wish that it is easier, but the fact that there is a result that for 9, it's not easier does make one wonder if it actually should be easier just for 2 with no coefficient. I would hope so. I'm an optimist, so I am hopeful, but we really do not have a good handle on how we should prove this so far.
Annie, I have also a question. I don't know if you mind.
Oh yeah, of course, please.
Yeah, thank you. Well, the first one is how difficult or easy is to check if a set has the Hadamard property. I don't know the complexity of that operation.
Well, for graph profiles in general, it's easy because we know the construction. I think that for combinatorial objects, like if you were looking at some combinatorial objects, you would usually have a pretty clear picture just by working with it quickly. Like, yes, it does. No, it doesn't. I don't know about complexity of it, but I think it's more like nice combinatorial properties generally that one has or one doesn't have.
I see. So is it easy, or how can we transfer the tropicalization of certain graphs that we already know, like what happens with the tropicalization? So I don't know, what happens if we take the Cartesian product of 2 cycles, or what's the problem, for instance, in that case, in that slide that you're showing us, with the even cycles or with the odd cycles? Why do you have to consider those graphs separately? There are many questions there, but
oh yeah. Okay, so why did we have to consider these apart? So we are trying to put them together, and there's this one inequality that we don't know how to prove, and I'm working on it. Hopefully I can prove it. If I can prove that one inequality, then we'll be able to put them together. But the thing about tropicalization is that somehow, yeah, we have these tricks to show like completeness, but to show that inequalities hold, we still need to use whatever standard tricks. You could use sums of squares, you can use entropy-based methods, you can use whatever you want, but you need something. And so the inequality that we're missing cannot be done with sums of squares, which is what I'm more familiar with. So I'm trying to learn entropy better so that I can try to do it choosing entropy. But that was the block there. Somehow we still need traditional methods to prove the inequalities in the first place. And then you were asking about, well, the Hadamard property talks about taking the product of graphs. So why aren't they in there? Like you would want to add them to those sets. Yeah, no, unfortunately, that would make it much harder. I mean, you would need completely new inequalities and whatnot, which maybe it would be possible. Maybe it would not be as hard as I think it would be, but a priori it won't necessarily be easy.
I see.
So so inequalities involving graph densities or graph numbers, have been around for a really long time, like not always like under that name. And yeah, proving them in general is a big problem. So most cases that are known are about nice graphs. And so when you take products of graphs, it is nice in a certain way, but they're much more complicated graphs.
I see, yeah.
I have also one question. So just because you talk about simplicial complexes, so this is just I'm wondering about this. So if you look at the graph density, or graph density, if you look at this a subset of graphs instead of a whole set of graphs, all possible graphs, do we have anything interesting, anything simpler? If, for instance, maybe I can cast my question like this. So we can look at 2 manifolds, right? So 2 surfaces, and from 2 surfaces we can have triangulations. So, and this, I'm just trying to connect this to topology. So if we look at all possible triangulations of a 2 surface, and then look at the density graph, is there any result which gives us something simpler for the density graph, or I mean, this is something not quite related. I'm not sure if I'm clear with the question.
I mean, so I feel I'm hearing you say, look at the triangulation of some manifold.
Or maybe in simpler words, so I'm still looking at the density graph, but not for all possible graphs, only for a subset of them.
Oh, yes. Okay. Yeah, no, that is something that we wonder about. And it's not necessarily easier. And sometimes it makes it harder, or at least we don't have. So like, and again, it more or less often just comes down to proving inequalities. So how are you going to prove the inequalities if you're only considering certain graphs, right? So your target graphs, are restricted. And so then, if you're using sum of squares, then what that means is you're going to be modulo sum ideal. So you can use your ideal to add stuff to your sum of squares. But if you're not using sum of squares, then, well, I'm not an expert in anything else, but I imagine, yeah, it somehow you do get more freedom, but it's also just, you have more choices. And so depending on how you are using a computer to try to help you find your inequality, to prove your inequalities are right, it might be challenging. So you kind of need to have a good idea about what you need to do, because you're actually making things a bit harder for the computer.
Right, because yeah, I was wondering if there is a connection, and if we then we look at two surfaces, and from two surfaces we have triangulations. Then if we get something from all these triangulations in terms of the density graph, then there are some some of the topological invariance of the surface might affect the density graph. So that was something I was wondering about. But
yeah,
like that's not going to be an easy problem.
And there's definitely some people who what they really like to do is within graph profiles think about where certain types of graphs with certain properties will end up, right? So that is definitely a question that other people work on, which is very interesting. But I have very little idea when it comes to any of that.
Guys, I have to run, but I wanted to say, Annie, a very nice talk.
Thank you.
We're actually done with the seminar, and thank you very much again thank you, Annie, for accepting our invitation, and thank you for joining us. And please feel free to come next week with the second seminar. And Annie, you're more than welcome to join us if you want to. Thank you very much, and have a pleasant evening.
Yeah, thanks for having me.
Thank you.
Bye, everybody.
Thank you, Annie.
Bye.
Thanks.